Hello everyone, I am Ms. Sushma working as Assistant Professor in the Department of ECE in Institute of Aeronautical Engineering College. Today's section we are going to discuss about what is signal, what are the basic elementary discrete time signals and their representation and classification of discrete time signals. So what is signal? Signal is a function of one or more independent variable which contains some information that can be conveyed, displayed or manipulated. A signal is nothing but it carries some kind of information. So examples of signals are voice signals, video signals, image or biomedical signals and telephone wires. Signals on the telephone wires or radar signals. So here signals may be one-dimensional signal, or multi-dimensional signal. If signal dependent on the one variable, then it is defined as one-dimensional signal. If the signal depends on more than one independent variable, then the signal is called the multi-dimensional signal. So for one-dimensional signal, for example, I am representing x of t. So the signal x depends on the independent variable time t. So here t is the independent variable. Whereas x is the dependent variable. For a multi-dimensional signal, example is grayscale image. Here the brightness of the image depends on the two space coordinates f of x comma y. So here both x and y are the independent variables. F is the dependent variable. So the signal here depends on the two space coordinates. That's why it is a multi-dimensional signal. According to the nature of the signals, based on the time domain, the signals are classified into continuous time signal and discrete time signal. So the continuous time signals are nothing but here the signal is defined as continuous in time and as well as continuous in amplitudes. It will be continuous in time as well as continuous in the amplitude. That signal is called as continuous time signal. Here the continuous time signal, we can define the signal every instant of time. Whereas in discrete time signal, the discrete time signal is defined as it is in the discrete is in the time domain. X-axis is represented as n, y-axis is representing m is x of n. Okay, here for discrete time signal, it is in the discretized in the time and continuous in the amplitude. Okay. Then here discrete time signal will be again classified as discrete time signal as well as digital signal. So after sampling the continuous signal, we will get the discrete signal which will be in discrete in time and continuous in amplitude. After quantizing, we will get the digital signal. Here both amplitude and time are in the discrete in the nature. This is digital signal. So the basic difference between the continuous time signal and discrete time signal and digital signals are In continuous signal, the both time and amplitude are in the continuous, whereas in discrete signal, the time domain is in the discretized form and the amplitude is in the continuous form, whereas in the digital signal, both time and amplitude are in the discrete form. So in continuous time signal, we can define the signal every instant of time, whereas in discrete signal, we can define the signal at the particular instance of time. Okay, this is the difference between the continuous time signals and discrete time signals. So the basic discrete time signals are defined, yet discrete times are known as discrete signals. So here for continuous signal, we will represent it is with the x of t. Whereas in discrete signal, we will represent that signal with the x of n. N should be the integer. So here we can represent x of in the sequence like, for example, 2, 3, 1, 2, 3. So these are the samples values for the particular sample interval. So this arrow mark indicates the defined as x of n, yet the n is equal 0, and the left side indicates n value will be the -1, -2, and right side the n value will be the 1, 2. So yet n is equal 1, the value will be the 2, yet n is equal 2, the value will be the 3. So in the graphical representation of this signal, we can write x-axis with the n and y-axis with the x of n. So this arrow indicates the value, yet n is equal 0. So the n is equal 0, the x of n value will be 1. So it is 1, yet n is equal 0. Yet n is equal 1, the value is equal 2. And yet n is equal 3, the value will be 3. The left side of the arrow mark indicates the negative sample value. So n is equal -1, the value will be 3. N is equal -2, the value will be 2. So this is the graphical representation of the sequence. So the basic discrete time signal, basic elementary signal, here now we are going to know the representation of basic elementary discrete time signals. These are the types of the discrete time signal. The first one is unit step function, unit impulse function, ramp sequence, parabolic sequence, signum function, exponential function, complex exponential, rectangular sequence, triangular sequence, sinusoidal sequence, SINC function, sampling function. So first we are going to discuss about the unit step sequence. So here the unit step sequence is denoted by u of n. It will be denoted by u of n. Here the u of n is defined as for n greater than or equal 0, the value will be 1, otherwise it will be 0. For normal step function, we can define that as u of n is equal a for n greater than or equal 0, and for n less than 0, it will be 0. For any unit functions, for example, unit step function, unit ramp, unit impulse, the magnitude of that signal will be 1. Okay, so that's why here unit step function, the magnitude will be, amplitude will be 1 for n greater than or equal 0. For n less than 0, it will be 0. So for the sample values for n is equal 0 to infinity, it will be 1. The amplitude samples will be the 1. Otherwise, it will be 0. Okay. So similarly, the shifted unit step function u of n minus k is defined as, here u of n minus k is defined as, for n greater than or equal to k, the value will be 1, otherwise it will be 0. So the value will be started from k. So from k to infinity, the value will be 1, otherwise it will be 0. For example, I want to denote u of n minus 3. So for u of n minus 3, for n greater than or equal to 3, the sample value will be 1, the amplitude will be 1, otherwise it will be 0. For n less than 3, it is 0. So I can denote that as x-axis it will be n, y-axis will be u of n minus 3. So for n greater than or equal to 3, the amplitude will be, the sample value will be 1. So for n is equal to 0, 1, 2, 3. So from 3 onwards, the sample values will be 1. Otherwise, u of n minus 3 will be 0. For n less than 3, it will be 0. So it will be left shifted by the 3 units for the u of n minus 3. For example, for normal step sequence, we can define u of n is equal to, for n greater than or equal to 0, for n less than 0, it will be 0. That is nothing but the sample amplitude value will be of the samples will be 2 for n greater than or equal to 0, otherwise it will be 0. Okay. Unit impulse sequence. So here the unit impulse sequence will be denoted as del of n. Del of n will be the magnitude of the sample will be 1 for n is equal to 0. For n not equal to 0, it will be 0. So this is the graphical representation of impulse signal. Here for n is equal to 0, the sample value will be 1. Otherwise, it will be, the sample value will be 0. So the shifted unit step function del of n minus k is defined as, for n is equal to k, the value will be 1, and for n not equal to k, it will be 0. Nothing but for the k value, the amplitude of that impulse will be 1, otherwise it will be 0. For example, I want to denote del of n minus 2, the nothing but it will be 1 for n is equal to 2 and 0 for n not equal to 2. So that will be, we can write that as, we can represent that as it n is equal to, the value will be, the impulse signal will be 1, the magnitude, and otherwise it will be 0. Ramp sequence. Here, a discrete unit ramp function can be defined as, here for n greater than or equal to 0, it will be n, and for n less than 0, it will be 0. It will be denoted by r of n. So the graphical representation of ramp signal will be, for n is equal to 0, substitute for here n is equal to 0, n value is 0. So the value will be 0. And for n is equal to, the amplitude will be 1. So the value will be 1. For n is equal to, it will be 2. And for n is equal to 3, it will be 3. So here the ramp signal is defined as r of n is equal to n for n greater than or equal to 0 and 0 for n less than 0. And rectangular sequence is denoted as rect of n here. And the length will be, length of the rectangular sequence will be denoted by the L. Here the sequence will be represented as rect of n will be 1 for n is equal minus L of minus 1 by 2 to L minus 1 by 2, 0 for all other n values. Okay, nothing but if I want to represent with the length L is equal to 7, I want to represent the rectangular sequence with the L is equal to 7. So that will be represented as rect of n will be 1 for, n will be minus L minus 1 divided by 2 to L minus 1 by 2. So minus of 3 minus 7 minus 1 by 2 to 7 minus 1 by 2, that is nothing but minus 3 to 3, it will be 1, all other n values, it will be 0. So nothing but here n, x-axis is n, y-axis is rect of n, from minus 3 to minus 3 to 3, the samples value will be 1. Remaining samples will be 0. So, this is the rectangular sequence representation. Parabolic sequence. Here, the discrete parabolic sequence will be denoted by P of n. It will be P of n is equal to n square by 2 for n greater than or equal 0 and 0 for n less than 0. So, here the parabolic sequence will be represented here. For n is equal 0, 0. For n is equal 1, it will be 1 by 2, that is 0.5 value. And for n is equal to 2 square by 2, it is 2. So, it will be represented by parabolic sequence representation. If you want to shift this parabolic sequence by 3 units, then it will be defined as, it will be n square by 2 for n greater than or equal 0 and 0 for n less than 0. So, it will be shifted by 3 units to the left side. So, it is starting from 0, third sample. Okay, it is shifting by 3 units to the right side. Then it will be represented by P of n minus 3. Signum function. So here the signum function can be defined as signum of n will be, for n greater than 0 it will be 1 and for n is equal 0 it will be 0 and for n less than 0 it will be minus 1. So for signum function, this is the signum of n. For this is the sample value. For n is equal 0, the sample value will be 0. For n greater than 0, the magnitude of the signum function will be 1. For n less than 0, the magnitude of the signum function will be minus 1. So, this is the signum function representation. Complex exponential sequence. So, here the complex exponential sequence will be defined with the two types, complex exponential sequence as well as real exponential sequence. In a complex exponential sequence, x of n will be defined as e power j omega naught n, where e power j omega naught n will be represented as cos omega naught n plus j sin omega naught n. So, it has real part as well as imaginary part. Whereas in real exponential sequence, it will be defined as x of n is equal c into a power n, where c and a both are real functions. Both are in the real. So, here then x of n is a real exponential sequence. So, here we have the 4 different cases here. It depends on the a value. Okay. If a greater than 1, that signal will be represented x of n is equal here c into a power n. So, if a greater than 1, it is exponentially increasing. If a between 0 to 1, it will be exponentially decreasing. If the a value is from minus 1 to 0, it will be represented as this one. If it is less than minus 1, it will be represented as this one. So, here in real exponential sequence, it will be x of n is equal c into a power n, where both c and a are real values. Sinusoidal function, here it will be represented as x of n a into sin omega n plus phi. So, here omega is the angular frequency, phi is the phase of the signal, it will be denoted as the sign discrete values of n value. Triangular function will be denoted as x of n is equal to a into 1 mod n greater than n, where n value will be n is equal minus n minus 1 by 2 to n minus 1 by 2, 0 otherwise. Okay, so here the signal, by seeing signal, it will be, we can represent denoted as it is a triangular signal. So the length, if I suppose I am considering a number of samples, length is represented by capital N, that will be 7. So the sequence will be started from minus 3 to 3 because it is minus n minus 1 by 2 to n minus 1 by 2. So the samples value will be starting from minus 3 to 3 to. SINC function. Here the SINC function is denoted as SINC of n. It will be sin pi n by the pi n. So it has main lobe as well as side lobes. The SINC function will be has the main lobe as well as the side lobes. So here now next we are going to discuss about the signal classification. Based on the nature of the signals are classified into continuous time and discrete time signals, deterministic and non-deterministic signals, and even and odd signals, periodic and aperiodic signals, energy and power signals. So first we are going to discuss about the continuous time signal and discrete time signals. So a signal is said to be continuous time when it is defined for every instant of time. Okay, so here the real-time examples of continuous time signals are telephone signals, speech signals, video signal, and every natural signals are continuous time signals. So it will be denoted, x-axis will be denoted here with the time, and y-axis it is denoted by f of t. Suppose for example x of t is equal sin t. It is a continuous signal, so it will be represented, x-axis will be in the time, y-axis is x of t. This we can define like this, but it is in the continuous time signal. Whereas discrete time signal, a signal is said to be discrete time when it is defined for particular interval of time. So here, after sampling the continuous signal, we will get the discrete signal. By multiplying the continuous signal with the impulse signal, we will get the sample value of the continuous signal. So here it will be represented by the x of n or y of n, f of n. So here n should be the integer value. So the particular value of integer values only we will define the discrete amplitude. Okay, a signal is said to be discrete time when it is defined yet only discrete instants of time. For example, in continuous signal, x of t and t, we can get the value here, the time t is equal 1.2 seconds or 1.2. Okay, so here the where is the 1.2, there we will get the amplitude value of that particular signal. Whereas in the discrete signal, we cannot get the value at 1.2. So it is 1, 2, 3, 4, 5. We cannot define the signal x of n at non-integer values. Okay. Deterministic and non-deterministic signal. A signal is said to be deterministic signal if there is no uncertainty with respect to its value at any instant of time. and it will be represented by the mathematical formula. Compulsory the deterministic signal will be represented by the mathematical formula. All u of n or del of n, sine omega n plus phi, all these signals will be deterministic signals. Non-deterministic signal is defined as if there is uncertainty with respect to its value at some instant of time is non-deterministic signal. We cannot define the signal. These are the random signal. For example, these non-deterministic signals also called as random signals. The examples of non-deterministic signal is the noise signal, and they are modeled in probabilistic terms. Even and odd signal. So a signal is said to be even or symmetric when it is satisfied with the condition x of n is equal x of minus 1. When a signal is satisfied the condition x of n is equal x of minus n, then the signal is defined as even signal, otherwise it will be odd signal. So a signal is said to be odd signal when it is satisfied the condition x of n is equal minus x of minus n. So it should satisfy the condition x of n is equal minus x of minus n. Then the signal is called as odd signal. So the examples for this even and odd signals are, for odd signals x of n is considered x of n is equal sine n. Substitute here x of n is equal sine of n. Substitute, replace n by minus n, that is x of minus n is equal sine of minus n. Sine of minus n is nothing but minus sine n. So this sine n is here, it is x of n. So here x of n is equal, we are getting minus x of minus n. Then this x sine of n will be the odd signal. Okay. Another example I am taking as x of n is equal cos n. Here x of, replace n by minus n here, x of minus n is equal cos minus n, and x of minus n is equal, cos minus n will be the cos n, that is nothing but x of n. So here x of n is equal to x of minus n we are getting. So this signal is called as even signal. Another, if I take the graphical representation of any signal, for example, I am taking the signal, x-axis is n, y-axis x of n, for n is equal 0, the sample value will be 0, and for n is equal 1, it will be 1, for n is equal 2, it will be 3, for n is equal 3, it will be 3. This is, for n is equal minus 1, it will be 1. N is equal minus 2, the amplitude will be 2. For n is equal 3, amplitude will be 3. So here I am taking this signal, whether it is even or odd. How we have to check this sequence whether it is even or odd. So here by seeing this picture, observe for x of 1, x of 1 is equal 1 and x of minus 1 value also 1. So x of 1 is equal x of minus 1. And x of 2 is equal to x of minus 2. The amplitude value will be 2. For x of 3, it is x of minus 3. The amplitude value will be 3. So here by seeing these values, we can represent x of n is equal to x of minus n. Okay. So this is the, it is satisfying the condition of x of n is equal to x of minus 1. That's why it is the example of even signal. For example, if we take the another signal, here this is x-axis 1, y-axis x of n minus 1. Here for n is equal to 0, it will be 0. So here for x of 1 is equal, we are taking this as x, for x of 1, is equal, the value will be 1. For x of minus 1, the amplitude value will be minus 1. So here x of 1 is equal minus x of minus 1, x of 2 is equal minus x of minus 2, and x of 3, the amplitude value will be minus 1. Here x of 3 it will be 1. So x of 3 is equal x of minus 3. So it is satisfying the condition x of n is equal minus x of minus n. Then this signal is called as odd signal. Even and odd components of signal. So every signal here x of can be represented as sum of even and odd components of the signal. So x of n will be the sum of even components of the signal as well as odd components of the signal. So to find the even signal components, the formula will be 1 by 2 x of n plus x of minus n. To find the odd signal components of the signal, the formula, it is denoted as x naught of n. The formula will be 1 by 2 x of n minus x of minus n. So periodic and aperiodic signals. A signal is said to be periodic signal if it satisfies the condition x of n is equal to x of n plus n. So it will be repeated for every instant of time period, particular time period, the signal will be repeated in sequences. Then the signal is called as periodic signal. Otherwise, it will be aperiodic signal. So for aperiodic signal, x of n is not equal to x of n plus 1. So the samples values will not be repeated after particular time period for aperiodic or non-periodic signal. But for periodic signal, the samples will be repeated for particular time period, fundamental time period. So after 3 samples, again the values are repeating. So after particular time period, the samples values are repeating in the periodic signal, whereas the aperiodic signal, the values will be not be repeated after particular time period in the aperiodic signal. Okay, here n is the fundamental time period and f is the fundamental frequency. So for example, here I am taking x of n is equal cos 2 pi f naught n plus theta. Okay. So for periodic signal, it should satisfy the condition x of n is equal to x of n plus n. Capital N is the fundamental time period here. So I am substituting here n plus capital N in the equation 1. Okay. Here it will be cos 2 pi f naught n plus capital N plus theta. This we can write as cos 2 pi f naught n plus 2 pi f naught capital N plus theta. So whether to get the x of n as periodic signal, it should satisfy the condition x of n is equal to x of n plus 1. When we will get this cos 2 pi f naught n plus 2 pi f naught capital N plus theta, as we should get as this as cos 2 pi f naught n plus theta. When we will get this, means this function will be multiples of 2 pi f naught n should be the multiples of some integer value. Okay, some integer value. So that's why I am taking as 2 pi f naught as 2 pi k, multiples of 2 pi. Multiples of 2 pi here. So we can write 2 pi f naught as 2 pi and f naught n we can write as k, and f naught is equal we can write as k by n. So it should be the fundamental frequency of that particular signal should be the rational value, then only that signal will be periodic signal. Otherwise, it will be aperiodic signal. For example, I am taking cos 2t. Okay, so here this value will be 2 here. This should be represented, frequency will be represented in the rational value. Both k and should be the integer here. Then only it will be periodic signal. Otherwise, it will be aperiodic signal. So, for function, we can write this as 2 by 1. So, it is a rational number. So, it is a periodic in nature. Otherwise, it will be aperiodic signal. Energy and power signals. So, here a signal is said to be energy signal when it has finite energy. So, it should be has the finite energy. Then that signal is called as energy signal. The formula for energy signal will be for n is equal minus infinity to infinity, mod x of n should be x of n whole square. Okay. For energy signals, the average power will be 0. For energy signal, the average power will be 0. So, for power signal, it is defined as the power signal has the finite average power. Then that a signal has a finite average power. Then that signal is called as power signal. For power signals, the energy will be infinity. Okay, the formula for power is average power is limit n minus infinity 1 by 2n plus 1 sigma n is equal minus n to n mod x of n square. Okay, so here we have to remember 3 conditions for energy signal. For energy signal, the energy will be finite value and average power is equal 0. And for next power signals, average power will be finite or non-zero value, and the energy of that power signal will be infinity. If both power and energy, average power and energy of the signal is infinite, then that signal is defined as neither power signal nor energy signal. So, these are the classification of discrete time signal. In next session, we are going to discuss on the what are the operations are going to perform on the discrete time signals. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.